And ladies and gentlemen, I don't really have much to say about this comic strip other than I appreciate its nerdiness and hope that you will too. Alright, today we wrap up the final section in Chapter 8 for improper integrals. We're going to talk about infinite limits of integration. That is, in fact, what makes, at least one of the things that makes an integral improper is if you have infinite limits of integration. Also, it will be improper if you have integrands with infinite discontinuities. And then we'll talk a little bit more about convergence and divergence. Alright, integrals with infinite limits of integration are improper integrals. Ladies and gentlemen, it seems like a small thing, but on the AP exam, I know that those who grade will take off points if you leave, and I don't know if you can see here because it's such small print, if you leave an infinity symbol in the integral as the integrand, the limits of integration, if you leave that in there, they will take off points. What we do is we back up because there we go. What we do is we use limits. We do a substitution. So, for instance, instead of saying a to infinity, I say a to b, and I do the limit as b approaches infinity. Now, technically, it's the same thing. But limits of integration are defined to be finite things, whether it's a variable or a number. It needs to be finite. So infinite is not finite, so we get around it by incorporating limits. Alright, I'll give you an example. Express the following improper integral in terms of limits, in terms of limits and of definite integrals, and then evaluate the integral. So the first thing we're going to do is we're going to get rid of this negative infinity to infinity. Now notice I've got two problems. I've got negative infinity and positive infinity. So first of all, we make two integrals. I split it up around 0. 0 is usually a good thing about which to split, although sometimes depending on certain discontinuities and troubles in the domain, we'll pick another number. But 0 is usually a good one. So I've split around 0. Now for each of those, I want to remove the infinity from the limit of integration. That's easy enough to do. I use a limit. The limit as b approaches negative infinity, the limit as b approaches infinity. Now if you want to change your variables so that they're not both b, that's fine. It's entirely up to you. Now we take the integral. The integral of e to the x is e to the x. And then you plug in your 0, and then you plug in your b and subtract. Same thing over here, plug in b, plug in 0. And of course e to the 0 is 1, so we make that simplification. Now we can plug in our infinities and our negatives. So I plug in negative infinity here, plug in positive infinity here. Now, e to the negative infinity, that would be 1 over e to the infinity, so that would be 0, and this would just be infinity, which means the 1's do nothing, and infinity is the answer. Alright, evaluating an improper integral from 1 to infinity. So now we only have one integral to deal with. Does the improper integral below converge or diverge? So we'll start with this. We'll again remove the infinity from the integral and set up our limit. Now, we know that the integral of 1 over x dx is natural log x. Normally I'll put the absolute values around the x, but it's not needed from 1 to infinity because that's positive. So I've got my integral there. Now, plug in my b and my 1 and subtract. So natural log b minus natural log 1. Of course, natural log 1 is 0, so it goes away. Now I can plug in my infinity, and I have natural log and infinity, and if you were to sketch the graph, you see that although natural log starts to level out, it never truly levels out. It keeps climbing forever and ever. So that would also be infinity. And if it is infinity, we know that that means that the function diverges. Alright, using partial fractions with improper integrals. Now these are always fun because this now is going to take 2 or 3 math problems and put them together in one. I have the integral from 0 to infinity of what you see there on the screen. Now, first of all, this is a partial fraction decomposition first, if you remember doing that not too long ago. So I'll factor the x squared plus 4x plus 3 to x plus 3x plus 1. And remember doing partial fraction breakdowns. I'll take the fraction that I have and I'll break it up into a over x plus 3, b over x plus 1. Multiply by the least common denominator on both sides and we get this. Now again, this is something we've done before, so I'm going through it quickly. Hope that you remember. If not, you can ask me about it tomorrow in class. If you plug in -3 for x, you can solve for a. If you plug in -1 for x, you can solve for b, and you get those numbers. And now this is my new integral problem. So I'll take the infinity out of the integral sign. I'll use my limit. The integral of -1 over x plus 3 is negative natural log x plus 3. You can get that by u substitution. Let u equal x plus 3. Similarly, the integral of 1 over x plus 1 is natural log x plus 1. Plug in your b's and your zeros, and we have this, natural log of b plus 3, natural log 3, and so forth. Let me move the screen down a little bit here. I can combine some of these things now. Remember, if it's positive, it goes on top, negative goes on the bottom. So that's positive, that's positive, well, that's 0. Natural log 1 is 0. We don't need to worry about it. So 3b plus 1 on top, b plus 3 on the bottom. If I distribute the 3, I have 3b plus 3 on top. Now I need to simplify, because if I plug in infinity right now, I get infinity over infinity. So there's a variety of ways. We could do L'Hopital's rule if you want. I can divide everything by b if I wanted to create this. I divided everything by b. If you like L'Hopital's rule, you could have done that. When I divide by b, I end up with this. Now if I plug in my infinity, that goes to 0, that goes to 0, and I'm left with 3 over 1. So natural log of 3. And of course, I didn't write it on the last slide, but if it goes to natural log 3, of course, you know that means that it converges. It does not go to infinity. All right, next one, using L'Hopital's rule with improper integrals. All right, so again, we'll start out by removing the infinity. You ought to be used to that by now. Set up your limit. I'm actually going to work this one out, first of all, as an integration by parts problem. If you remember integration by parts, I'll let u equal x, du is dx, dv is what's left over, e to the negative x dx, means v is negative e to the negative x. The antiderivative of e to the x is negative e to the negative x. And remember that integration by parts, the formula is uv minus the integral of v du. So all that together is integration by parts. Do you see how all the things that we have learned are now starting to come back together? Alright, so take my integral of e to the negative x. That's negative e to the negative x, and I now have this. The problem with that is, though, it's going to get messy if I try to plug in the infinity. So what I'm going to do, I know that e to the negative x I can move to the bottom and make e to the x on the bottom. So this would be negative x over e to the x. This would be minus 1 over e to the x. So I've already got them with a common denominator. I can put them together here, and it's going to simplify slightly what I do. I still end up with an infinity over infinity at this point. And as such, since it's infinity over infinity, of course, you know that we can fix that. We can plug things in. We can do whatever it is we need to do. But let's go ahead and take care of the b's first. Let's go ahead and plug in our b's before we worry about simplifying this. When I plug in my b and my 1, that gives me negative b minus 1 over e to the b. And then we have this part right here. We simplify. All of this part right here becomes 2 over e. Now that 2 over e is done. There's no variables left in which to substitute. But now if I look at this, I'd still have infinity over infinity, which is the same problem I had a moment ago. Okay? Again, you can take the time to split that up, and if you're doing the AP exam, it's good to do that so you can show people what you're doing. Applying L'Hopital's rule, the derivative of negative b minus 1 is just negative 1. E to the b stays e to the b. If I plug in my infinity now, this goes to 0 right here because I have infinity on the bottom. 0 plus 2e, or over e, is 2 over e. Alright, our next problem, ladies and gentlemen, we're going to evaluate an integral from negative infinity to infinity. We've already done one of these, but it's good to have another one. And you see we're taking the integral of dx over 1 plus x squared. Now again, as I mentioned earlier, we do want to split it up into two separate integrals so we can deal with one problem at a time. So I'll break it at 0 just because 0 is a good breaking point. Pull your infinities out of the integral. Use your limits. Now what about this 1 over 1 plus x squared? Well, I recognize that to be an arctangent. If you remember arctangent, the antiderivative of 1 over 1 plus x squared is arctangent. From 0 to b, b to 0. Plug in your 0 and your b's, as you see here. Now, we know that the arctangent of 0 is 0, so there and there. So we get rid of those. And now we're ready to take care of the infinity. So I plug this in. Now the question is, what is arctangent of negative infinity? What is arctangent of infinity? Well, that's very simple. The arctangent of negative infinity and infinity each are pi over 2, or negative infinity pi over 2. So this becomes negative pi over 2. So negative infinity was negative pi over 2. Positive infinity is pi over 2. And we know that because if you look at the graph of tangent, you have asymptotes at pi over 2, negative pi over 2. And that, ladies and gentlemen, would be infinite because you know the graph follows the asymptote up forever and down forever. So if I simplify that, I have pi over 2 plus pi over 2, which is just pi. Now, along with the infinite limits of integration, you also can have discontinuities. In other words, you can have domain problems within the integral. We solve these problems the same way. We remove the discontinuities and we use limits at whatever the discontinuity is. Alright, so first of all we look at this and we ask, what is the problem? Well, the problem here is 1. You see, I'm going from 0 to 3, but 1 is a problem because 1 minus 1 would be 0 on the bottom, so there's a problem there. So here's what we do. We set up an integral from 0 to 1. 1 becomes the breaking point, and then 1 to 3. Now remember, 1 is a problem because it gives me 0 on the bottom. So I pull the 1 out. 0 to 1, I approach 1 from the left. You know, starting at 0, moving toward 1 is from the left. Here I'm approaching 1 from the right, starting at 3 and moving back toward 1 here. Alright, we need to find the antiderivative of 1 over x minus 1 to the 2/3. Well, if you write it as negative 2/3 and then add 1 to the exponent divided by the new number, we get this, 3x to the 1/3. If you're not sure how I got that antiderivative, again, write it out or ask me tomorrow in class. But we do this, and we've got our b's and our 0 and our 3 and our b, and we plug all those numbers in. Plug in b, subtract, plug in 0, and so forth. And now we need to simplify. Of course, this minus a minus becomes plus, and that's 1 to the 1/3 times 3, and all that's 3. Over here, 3 minus 1 is 2 to the 1/3, and we have this. Now, what about the 1's here? Well, if I plug in the 1 for my limit, 1 minus 1 is 0. This part is gone. I'm left with 3. If I plug in 1 here, 1 minus 1 is 0. This part is gone. I'm left with 3 times 2 to the 1/3. Now, you can leave your answer like this, or you can leave it, you can rewrite it as the cube root of 2. Alright, what about this one? The integral from 1 to 2. Again, you see 2 is a problem because 2 minus 2 would be 0. So we'll pull that 2 out using a limit. The derivative or antiderivative of x minus 2 is natural log x minus 2. Again, I technically don't need the absolute value bars because starting at 1 and going up, I'm only going to have positive values. Alright, you can plug in your b minus 2, plug in your 1 minus 2 like that. Although I guess you do see because of the minus 2, it was important we kept the absolute value bars because of this situation right here. 1 minus 2 is going to go negative. So we end up with this. Now plug in your 2 for b. 2 minus 2 would be 0. 1 minus 1, this natural log of 1 here is 0 right here. And what is the natural log of 0? Well, natural log of 0 is negative infinity. Again, look at the graph. At 0, the graph of natural log drops down forever, so that's negative infinity. And I am very near the end of this first 15-minute video, so we're going to pause it, and we'll finish up the slides. There's not a whole lot left on the next.